Hello dear students, welcome back to my lesson. To continue the previous lesson in chapter 6, section 1, the angle on today's lesson we're going to talk about the angle between magnetic field and a circuit effect is the induction, okay? So as you learned it in the previous lesson, one way to induce electromotive force in a closed circuit or in a closed loop of wire is to move all or part of the loop into or out of the constant magnetic field as follows. According to Faraday's law, electromotive force is equal to negative N change in flux per unit of time. N is number of turn and this is change in flux per unit of time. So as you know that the flux is also equal to what? This flux equal to what? Is equal to AB cosine theta. As you learn it, A is the area vector, B is the magnetic field strength of the magnetism, and the theta is the orientation of the coil. The orientation of the coil is very important for induction of electricity or induce the electricity. Now, okay, so we have note here, the magnitude of induced EMF and the current depends partially on how the loop is oriented to the magnetic field as shown in the figure below. So this is very important. The magnitude of induced EMF and the current partly on how to the loop is oriented to the magnetic field. So it means that the orientation of the coil is very important. Look at this figure, we have three parts here. In this figure, as you can see, the coil is the plane of the loop or the plane of the coil is perpendicular to the magnetic field. Okay, and this figure, the plane of the loop is what? Is perpendicular to the magnetic field. But it is area vector. This is the area vector. It is area vector is parallel. So it means that when the plane of the coil is perpendicular to the magnetic field, its area vector is parallel, and this angle is equal to 0, and the angle of what? Area vector. Okay, so we have to take the angle of area vector, not the plane of the loop. Okay, so in that case, how many field lines crosses the coil? This is the maximum field lines that crosses the biggest number of lines crosses this coil. It means that the magnetic flux has maximum value when the plane of the loop is moving perpendicular to the magnetic field. In this case, when the angle is tilted, in the case of tilted angle, when the plane of the loop makes an angle to the electric field, so in that case, the plane of the loop is not parallel and not perpendicular, it's tilted angle, okay? Also in this case, the angle should be given in the question to find the induced EMF or magnetic flux. In the case when the plane of the loop is parallel, look, the plane of the loop is what? Is parallel. When the plane of the loop is parallel, like for example, this is magnetic field line, okay? This is magnetic field lines. If the coil is parallel, if the plane of the loop is parallel, no magnetic field lines crosses the coil. It means that no change in magnetic flux. There is no change in magnetic flux. There is no crossing magnetic field lines to the coil, and no current is induced here. Now, this is the plane of the loop. Plane of loop is parallel. When the plane of the loop is parallel, the area vector is what? This is area vector. The area vector is perpendicular. When the area vector is perpendicular, it means that the angle between magnetic field line and area vector is 90. According to the equation of magnetic flux is equal to what? AB cosine theta. So in that case, the magnetic flux is equal to what? Is equal to 0. Why? Because the angle is equal to 90. Cosine 90, as you know, is equal to what? Equal to 0. Okay. In the case of, I'm going to repeat the first case, when the plane of the loop is perpendicular. Look, assume that this is the magnetic field lines. What is this? This is magnetic field lines. Okay. This is B. Okay. If the coil is oriented it is plane or plane of the loop perpendicular to the magnetic field, the figure should be like that. Look, in that case, how the coil is oriented in this magnetic field, so you have to consider that this is the plane of the loop. The plane of the loop, is perpendicular. Perpendicular to what? To the magnetic field. When plane of the loop perpendicular to the field, it means that its area vector is parallel, because area vector and plane of the loop is always perpendicular to each other. When plane of the loop is perpendicular, area vector is parallel. When plane of the loop is parallel, area vector is perpendicular. So according the equation of Laplace is equal to AB cosine theta. So what is this angle? The angle between A and B. Where is area vector in this case? The area vector is located here. This is area vector. What is this? This is area vector. Look, area vector and magnetic field are parallel to each other. Area vector with magnetic field are parallel to each other, and the angle is equal to what? 0. Cosine 0, 1, maximum. Flux is equal to what? Maximum. When the flux is equal to maximum, the change flux also becomes maximum, and induced EMF becomes maximum. In the moving coil, according Faraday's law, when does the induced EMF or the induced potential difference and current becomes maximum value? You have to say when the plane of the loop is perpendicular and the area vector is parallel. In that case, the EMF is equal to maximum. So when does EMF for moving coil? When does EMF equal to 0? You have to say when the plane of the loop is perpendicular, when the plane of the loop is parallel to the magnetic field. Okay. Okay. Look here. This is plane of loop parallel, tilted angle, and this is perpendicular to each other. Okay. If the plane of the loop is perpendicular to the magnetic field, or magnetic field is parallel to the area vector, most magnetic field lines passes or cut through it, through the coil, and the induced EMF and current, induced current will be maximum. Okay. So if the plane of the loop is tilted, look, the induced EMF and induced current, it becomes smaller or between maximum and 0. Okay. And if the plane of the loop is parallel, like this figure, no magnetic field line is crossing the loop and no flux will occur. In that case, and EMF is equal to 0. We have a question here. Why does a loop that is parallel to the field? What do you mean by the loop is parallel? It means that the plane of the loop is parallel. When the plane of the loop is parallel, the area vector is perpendicular. Cosine 90, 0. And loop is shown in this figure below. Experience no current around the loop even though the loop is moving. In the case when the loop is moving but no current is induced, no potential difference is induced. The answer is because the electrons do experience a magnetic force perpendicular to the field. When the charge is moving parallel, according to the magnetic force is equal to what? QVB sine theta. Sorry. QVB sine theta. Look, magnetic force is equal to QVB sine theta. When the charges or when the charged particle on the conductor moving in parallel, angle 0 between V and B, and there is no magnetic force here and no induced potential difference and no induced current. Okay, so the electrons do experience only on a magnetic force perpendicular to the field, not parallel to the field. But they cannot move in that direction because the plane of the loop is parallel to the field. So we have some notes here. The role of that the orientation of the loop plays in the inducing the current can be explained by the force that the magnetic field exerts on the charges in the moving loop. Only which component? Only the component of the magnetic field perpendicular to both the plane and the motion of the loop exerts a magnetic force on the charge in the loop. Look, in that case, which component produces the induced current and experience a magnetic force? The perpendicular component, B cosine theta, not the parallel, okay? And no EMF is induced if the loop is static. If the loop is static, there is no relative motion, as you know. In the case when there is no motion, there is no relative motion between the coil and the magnetic field, no current is induced, no EMF is induced. And if the magnetic field is constant, why? Because when the magnetic field is constant and the coil does not moving, no current is induced. When the induced electromotive force occurs, a current is induced in the closed circuit. When does the current is induced? In closed circuit or open circuit? In closed circuit. We have a question here. The magnitude of the induced EMF and the current depends partly on how the loop is oriented to the magnetic field. What happens if the plane of the loop perpendicular to the magnetic field? We studied. If the plane of the loop perpendicular, the EMF and current becomes maximum. If the plane of the loop is tilted between maximum and minimum. If the plane of the loop is parallel, no current is induced here. For branch C, EMF is equal to 0, current also equal to 0. Why? Because the plane of the loop is what? Parallel. Angle is equal to what? 90. Cosine 90, 0. Change magnetic flux is 0. Induced EMF also 0. Okay. Change in the number of magnetic field line induces a current. One way to predict whether the current will induce in a given situation is to consider how many magnetic field lines cut through the loop. More magnetic field lines cross the loop, more flux changes, okay? And more EMF is induced. For example, moving the circuit into the magnetic field causes some lines to move into the loop. Changing the size of the circuit, area of the circuit, or rotating the loop changes the number of the field lines passing through the loop. How can you change the line passes through the coil? By changing the area of the coil and rotating the coil into the magnetic field. As does changing the magnetic field strength or direction. Figure shown below summarizes these three ways of inducing current. What are the ways of inducing current and EMF in a circuit loop? By 4 ways, we can induce the current in the circuit. The first one, moving a circuit loop into or out of the magnetic field, either the circuit or magnet moving. Look at, such as this experiment, moving the magnetic field into the coil or coil into the magnetic field. In the case when both magnetism and coil are at rest, there is no current induced. No shining of the light bulb, no deflection of the needle. But in the case when we approach the magnetism, what happens? The light shining and the needle deflected. At rest, no deflection of voltmeter, no shining of voltmeter. In the case when we move away, decreasing the magnetic field, the flux changes, also the current is induced, okay? This is the first way. The second way, rotating the circuit loop into the magnetic field. We will study in detail in section 2 about the generator. When the coil is rotating, this rotation of the coil, it goes to changing the magnetic field lines that cutting the circuit, okay? And also it goes to changing magnetic flux. Changing the angle between what? Area of the circuit and the magnetic field. The third way, changing the size of the circuit. By changing the size of the circuit, also the magnetic flux changes. When the magnetic flux changes, the EMF is induced. The last way, changing the magnetic field strength. So it means that if we change the magnetic field strength like the electromagnetism, okay, if we have a circuit with the coil and increasing by rheostat, increasing current and decreasing current, increasing and decreasing current, it goes to increasing and decreasing the magnetic field. When the magnetic field increases, what happened to the magnetic field line is also increases. What happened to the change in magnetic flux also increases, and induced EMF will be more. Okay, and it is direction or both of them. So the changing the direction of the magnetic field also can produce the change in magnetic flux and induced EMF, such as this experiment. Look, if we set the magnetism into the coil and at rest, in that case, without moving the coil and magnetism, how can you induce the current and EMF? By changing the direction of the magnetic field. By changing what? The direction of the magnetic field. So it means that when we change the direction of the magnetic field, also it goes to changing the magnetic flux. Look, by changing the poles of the magnetism, its direction will be changed. Look, without moving. So what do you mean by that? It means that we can induce the current without moving, but by changing the poles of the magnetic field. Okay, so this is according to the figure. In the first one, moving the coil or the magnetic field into the fields, the current is induced. The second one, rotating the coil into the magnetic field. This figure, look, how can we induce the magnetic field without moving? Only by increasing and decreasing magnetic field. Look, we have more fields here and we have less fields here. By changing this field, increase and decrease of the magnetic field, it causes to change magnetic flux. Okay, and this is by changing the area of the loop. Okay, so that's all for today. Inshallah, we will continue in the next lesson. Hope you enjoy and get benefits from my lesson.